Hey folks, this is the first page for the first video on the series that goes along with the notes for example 2, rotation and deflection notes. This video and the page accompanying it goes with finding the shear functions for these for this beam. This is part 1 of example for deflections and rotations 2. In this part we'll go through the reactions and the shear and moment diagrams for the beam in question. We've got this beam that has a uniform load distribution of 1.5 kips per foot. We have a pin at A and a roller at B. We have the Young's modulus and the second moment inertia constant and known. So if we want to know the deformation and the rotation of this beam, then we're just going to need to know the reactions. So the way we're going to do that is the same way we've done it since last semester. We're going to say the summation of force in the y direction had better sum to 0 because we're not accelerating upwards. And that's going to be equal to the reaction at A in the y direction plus the reaction at B in the y direction minus our distributed load, which is 1.5 kips per foot times the 12 feet that's active over. And we've got our moment equation. Let's specify which direction we want to be positive. Summation of moment. Let's take the moment about A. That's also got to sum to 0. That's going to be 9 feet times the reaction at B in the y direction minus, because the distributed load is going to cause clockwise rotation, the magnitude of that load is going to be 1.5 kips per foot times 12 feet, and the lever arm for that is going to be 6 feet, which is 1/2 of the full 12. We've only got one reaction going on here, so this one, if we just solve it out, that's going to go ahead and tell us immediately that the reaction at By is going to be 12 kips up. And now that we've got that, we can plug that right back in there. We can find that the reaction A in the y direction is going to be 6 kips. Also up. So I guess let's redraw this as a free body diagram. We've got a force right here, 6 kips. We've got a force right here that's 12 kips, and then that distributed load still there. Oop, a little long. And that's still going to be W. It's 1.5 kips per foot. So now we want to know, we're going to want to set up the shear diagram. So we're going to want to use the equation that the shear is going to be the integral of the distributed load. Oop, D didn't look right there. Fortunately, our distributed load function is extremely easy. It's just a constant. It's not even really a function. So we're going to be able to say that from A to B, at B we're going to have a discontinuity on account of this this point load right here. We'll also have a discontinuity at A, but we can take care of that right away. Right, so from A to B, that's going to be the integral of 1.5 kip per foot d x, which is going to be 1.5 kip per foot. This is extremely important to maintain your units throughout, because this is given in KSI, this is given in inches to the fourth. These lengths are given in feet, so we're going to want to keep track of how much of this is done in feet and how much of this is done in inches. Times x, I'm going to call this x1. I'm going to have it start at A and progress to B. I'm going to define an entirely different x, x2. It's going to start at 0 at B. That'll make our later efforts easier. And we're going to have right here some constant of integration C1. Well, we've got this point load of 6, so we know that C1 has to be equal to 6 kips. So, from A to B, our shear function of x1 is going to be equal to 6 kips minus 1.5 kip per foot times x1. Alright, from B to C, though, is going to have that same behavior, right? But now we're going to have a different constant integration. We're going to get down to our constant integration, our point B, right? So we can plug in 9 feet for x1, and then remember that we're going to pop up 12 kips. So if we plug 9 into here, we're going to get negative 7.5 kips. Six kips minus 1 point kip per foot. That's 9 feet, and that'll give us negative 7.5 kip. But there's also a point load right here of 12 kips. So we're going to have a discontinuity. It's going to bring us up to positive 4.5 kips. So from, just a sec, from B to C, we're going to have our shear be a function of x2, and it's going to be equal to 4.5 kips minus 1.5 kips per foot, keeping track of all those units, times x2. And we need to be sure that if we plug in 3 feet, we end up with 0, because this is a free end. We sure as heck can't have any internal shear at the end of this. So plug in 3 feet to this, and we end up with 1.5 times 3 is 4.5. It's negative, so this does end up being 0 at 3 feet. Good.